Well, hello there, guys. Welcome to our last video of this unit on chemical quantities. It's 8.5, which means 8.5 for those of y'all who aren't bilingual like me. In this video, we're going to be learning about two new vocabulary terms that refer to how we come up with formulas. The first term you're going to learn is molecular formula, which I know is not at the top of the page. I'm just switching things up a bit, you know, just being crazy and starting in the middle of the page instead of the top. So look at, like, near the bottom, you'll see the term molecular formula, and next to it in red, I wrote the definition. For now, ignore everything that I wrote below it. Just look at the red definition. A molecular formula is essentially the formula of a compound as it exists in nature. It's essentially just the natural formula. So I have some examples here. Some examples that hopefully you're familiar with. The first one is sugar. Sugar's natural formula is C6H12O6. And some of you all might remember that from biology, but if you don't, just trust me on this. This is the molecular formula for sugar, or the natural formula. Water's molecular formula is H2O, meaning that it always exists in nature as two H's and one O bound together. Hydrogen peroxide's molecular formula is H2O2, which just means that the natural compound of hydrogen peroxide is made of two H's and two O's put together. And then I have a couple other examples. I have benzene, which is C6H6, and I have salt, which is NaCl. Those are all natural formulas, how they exist in nature. The next term I want to talk to you about is called an empirical formula, and that's at the top of the page. So we're just kind of going all over the place. So if you would go back up to the top of your page and write in this definition next to empirical formula. An empirical formula is not necessarily the natural formula. It's just the formula that's at the smallest ratio. What does ratio mean? Well, let's take a look at something easy like hydrogen peroxide, or H2O2. Hydrogen peroxide is made of two H's and two O's put together. That's the natural molecular formula. If I asked you to find the empirical formula for that compound H2O2, all we would do is we would look at the ratio. Right now we have two hydrogens for every two oxygens. Is that the smallest ratio, 2 to 2? No, we could reduce that ratio, right? We could reduce it down to what? We could reduce it down to 1 to 1. So the empirical formula for hydrogen peroxide would be HO. Basically, it's a 1 to 1 ratio. I was able to reduce it down. Now, HO is not how hydrogen peroxide exists in nature. So this is not the molecular formula, but it is the empirical formula. Let's look at another compound. Let's look at sugar. Sugar is made of 6 carbons, 12 H's, and 6 oxygens. That's how it exists in nature, the whole compound. But is that the smallest ratio that I can make for this compound? No, I could actually reduce this down, right? Right now the ratio is 6 to 12 to 6. What could I reduce that down to? I can reduce all of these if I divided all these numbers by 6. So my smaller ratio would be 1 to 2 to 1, right? So if that's my smaller ratio, then my empirical formula would just look like this: C1H2O1. So that empirical formula is different from the molecular formula. Remember, molecular formula is how it exists in nature. Empirical formula is just the smallest ratio. Now let's look at a couple others. Let's look at water. Water's molecular formula, or how it exists in nature, is H2O, right? H2O. That's how we see it in nature. Well, what would it look like if we wrote the empirical formula? Well, right now the ratio is 2 to 1. Can you reduce a ratio that's 2 to 1? You can't, right? You can't get the number 1 any smaller than it already is. So we have to keep the ratio 2 to 1, which means the empirical formula is the same as the molecular formula. Now, how can that be? Well, sometimes a compound can exist in nature in the lowest ratio. For example, water only has 2 hydrogens connected to 1 oxygen, and that just happens to be the lowest ratio. So sometimes a molecular formula can be the same as its empirical formula. Let's look at benzene. Benzene's formula is C6H6, And so if I asked you to write the empirical formula for that compound, right now it's at a 6:6 ratio. We can reduce that down to 1:1. So if we reduced it to 1:1, it would look like this, CH. That would be the empirical formula for benzene. And then lastly, let's look at salt. Salt's formula is NaCl. It's at a 1:1 ratio. We can't make that any smaller than it already is. So the empirical formula and the molecular formula are the same for NaCl. We can actually calculate the empirical formula for any compound if we're given the percent composition of each element in the compound. The problem is that you need the percent composition of every element. We're not given the percent composition of oxygen. Well, what do we know about percent comp? We know that all the parts have to add up to a whole, right? Well, I have one part here, and my last part I don't have. So if I added these two up and subtracted them from 100, I would be able to find my percent composition of oxygen. So if I take 67.6 and I add it to 10.8, I get a total percent composition of 78.4%. So that means oxygen has to be the remaining percent. So I'm going to take 100 and subtract it from 78.4 and I get 21.6%. So 21.6% of the compound is oxygen. Remember, the first thing is you need to have the percentages of all of your elements. Now that we have the percentage of all the elements, I can find the empirical formula of this compound by following these steps. So to help you guys out, I've reached down into the creative depths of my soul and created a rap for you. Are you ready? Okay, someone drop a beat for me. Percent to mass, mass to moles, divide by small, multiply till whole. I know, I'm a lyrical genius. So let's get started. First, percent to mass. We're going to take the number that's a percentage and we're going to pretend that that's the mass of the element. For example, we have 67.6% mercury in this compound, so we are going to change that and we're going to say that we have 67.6 grams of mercury. Essentially, we're going to pretend like we have 100 grams of this compound. And so if we had 100 grams and 67.6% of that was mercury, then we know we have 67.6 grams of mercury. So you take the percentage and you change it to grams. That's the first step, percent to mass. So you need to have masses. Now you might have a problem where you get to skip the step. For example, if the problem does not give you percentages, but it gives you grams, then you just go with the grams, okay? You don't have to do this step. The second step is we have to take each of these masses and we have to convert them to moles. And that should be pretty easy. That's just a one-step conversion, just like what we learned last in the previous videos. So if I have 67.6 grams of mercury and I want to find moles of mercury, we're going to do this for each element. Okay, I have to set up a T-chart, right? And I have to convert from grams to moles. So since grams is on the top, I'm going to put grams of mercury on the bottom. And my molar mass for mercury, I just look on the periodic table, and it is, ooh, it's really big. It's 200.6 grams of mercury in 1 mole of mercury. So I'm just using my molar mass conversion. I put the grams on the bottom so that they can cancel, and I'm left with moles on the top. So I know I set it up right. So essentially this problem is just 67.6 divided by 200.6. That gives me 0.34 moles of mercury. So I've done grams to moles of mercury, and now I need to do grams to moles of sulfur. So I have 10.8 grams of sulfur over 1, and I'm converting to moles of sulfur. So I need to use my same conversion factor. That's molar mass. I'm going to put the molar mass of sulfur on the bottom and 1 mole of sulfur on the top. The molar mass of sulfur is 32.07 grams in 1 mole. I cancel out of grams, so I'm left in moles. And when I do this math, I get 1.35 moles of oxygen. So I've done grams to moles. Sorry, that was supposed to be a check mark. So I've done step 1 and I've done step 2. Step 3 is to divide by the smallest. So you have to look at these moles. You have to look at each of these numbers here, find out which number is the smallest. We have 0.34, we have 0.34, and we have 1.35. So which one's the smallest number? 0.34 is the smallest number. So I'm going to divide all of these by my smallest number. The smallest number is 0.34. So all of these are going to be divided by 0.34. I'm really doing this just so I can simplify my numbers. When I take 0.34 moles of mercury and I divide it by 0.34, I end up with 1 mole of mercury. If I do the same for sulfur, I get the same number, 1 mole of sulfur. When I take 1.35 moles of oxygen and I divide it by 0.34, then I end up with 3.97, okay, 3.97 moles of oxygen. Anytime you're at a 0.9, we're going to just round up to 4, okay? So we're actually going to pretend that this says 4 moles of oxygen. So we've done percent to mass. We converted all our masses to moles. We divided by the smallest, and then the last step is really just a step you do just in case your numbers aren't whole numbers. Are whole numbers, 1, 1, and 4. Since I have whole numbers, I don't have to do this step, okay? I get to skip it. If, however, these numbers right here are not whole numbers, for example, if you ended up with 2.5 for one of the moles, then since you ended up with 2.5, you would multiply every single one of these numbers here by this number 2 so that you could end up with whole numbers. But since all mine are whole numbers, then I'm done. I have 1 mole of mercury, so I do Hg1. I have 1 mole of sulfur, so I do S1. And I have 4 moles of oxygen, so it's SO4, which, hey, that happens to be a polyatomic, right? That's mercury sulfate. So that is how I get the empirical formula of a compound. I'm going to have you do number 1 on your own because it's very similar to the one I did. It already gives you percentages. But I am going to do number 2 with you. In this problem, remember how we go percent to mass, mass to moles, divide by small, multiply to whole. So I don't have to do the percent to mass part because guess what? I'm already given mass for each compound. So I start with, let's start with carbon. 2.61 grams of carbon over 1, and I'm converting to moles, right? It always goes percent to mass and then mass to moles. So my mass of carbon's on the top, so I want my molar mass of carbon on the bottom, and I want 1 mole of carbon on the top. I want my molar mass of carbon on the bottom so it can cancel out. My molar mass of carbon is 12.01, and so when I figure that out, it's 0.22 moles carbon. Okay, the next one I'm going to do is hydrogen. Hydrogen's molar mass from the periodic table is 1.01, and then cancel out of grams. Forgot to do that on this one. Whoopsies. And then I get 0.64 moles of hydrogen. And I have one more that I'm doing, that's oxygen. So I already was in mass, percent to mass, and then I did mass to moles for each one. So now I divide by small. So I look here, which one of these is the smallest number? 0.11 is the smallest number. So I'm going to divide all of these numbers, each one, by 0.11. This gives me 2 moles of carbon when I divide them. This gives me 1 mole of oxygen when I divide them. And this gives me it gives me like 5.9, which I'm gonna, I think it's 5.9, which I'm gonna round up to 6. Okay, so are all of these whole numbers? Yes, so I don't have to multiply any of them by a number since they're already whole numbers. So I have 2 moles of carbon, I have 6 moles of hydrogen, I have 1 mole of oxygen. See how these numbers right here, you're going to put as their subscripts, okay? And that's it for today. Guys, go ahead and try this one on your own, and then we'll go over it in class together. Y'all have a fantastic day, and stay cool.